Good afternoon, everyone. This is the last presentation, and our presentation is for the high flux, high resolution powder neutron diffractometry. And I'm Ray, and this is Corey. This is Liang. And this is the outline for our presentation. First, we will introduce HFIR beamline HB2A, and the second, we will see the applications of the neutron diffraction on the magnetic structures. And the last one is the recent progress on this beamline. And first, we will see this is reactors we have been seen before, and this is a beam at HB1 group. And this is what we have done as a high-resolution diffractometer, HB2A. And from this side, we can see the real picture of the detectors and the collimators. And the beam is come from direct to the monochromators, and there has a 90 degrees beam and then to scatter by the sample. The beam size is 25 by 25 square millimeters. And the scattering angle is from 0 to 155 degree, and the sample angle can be from 0 to 360 degree. And the resolution is pretty low, and it is good resolution, high resolution. And for the monochromators, they can use to generate the single wavelength neutrons. And they use 3 different planes to select the 3 different the wavelengths for these neutrons, 115, 113, and 117. Select 1.54 angstrom at 2.41 and 1.12 angstrom, 3 planes. And here is real-time the monitors to get the data. And this can be used on the website. You can see on the laptop and cell phone to monitor what is going on your sample on the experiment. And some capabilities for this beamline is they can do crystal structure refinement very accurate, and some phase transitions. And also they do the magnetic phase transition and magnetic phase separation, and also the density distributions. And also they can do the different temperatures at different pressures. They generate the phase diagrams, and also the temperature-dependent microstrain. They can get the stress strain. Also the in situ studies.
And then the next part, I'm going to talk about the experiment we done at the beamline. So, as we all know, neutrons can interact with the nucleus of the atoms and also the magnetic moment of the atoms. So in this case, from the scattering, we can learn the atomic structure and also the magnetic structure of a compound. In this way, we can have a whole picture of the crystal structure. And then we have a better understanding of the properties of the materials we are going to study. We did the structure analysis of nickel oxide through the powder neutron diffraction. The nickel oxide powder was loaded into the vanadium can, and this sample was heated, was scanned at a different temperature. Through the overlay of the temperature-dependent patterns, we can see at high temperature there are just a few strong peaks. Those peaks are the Bragg diffraction peaks of the atomic structure. And when we're cooling down the temperature to a certain point, some small peaks start to appear. And continue to cooling down the temperature, the peaks become stronger and stronger, and we can see more small peaks. If I zoom in the low angle part, the small peak, the intensity of the small peaks can be seen clearly, so the intensity is increasing. So if we take a close look at those small peaks, we can find out that the intensity, there's a trend of the intensity of those peaks. So we can say the intensity is decreasing with the increasing of the 2 theta, which is also the Q spacing because it is single wavelength. So we can say the intensity is decreasing. As we all know, the neutron scattering length of the is independent with the Q spacing. So it is So it is not the Bragg diffraction from the atomic structure. So when we're considering about the magnetic form factor, we find out that the nickel 2+ atom, the magnetic form factor actually it is decreasing with the increasing of the Q spacing. So those small peaks might be the magnetic ordering. So we are going to use we use the foolproof suit to solve both the atomic structure and the magnetic structure. Since the nickel oxide is a very simple compound, you can find the structure of this compound online very directly. So we load in the HFIR and did a river refinement. We can see those Bragg peaks can be fit very well. However, now those small peaks are indexed in this space group. Then we index those small peaks and do some calculation by the computer and some judgment by human being. And then we find out a space group which can be used to index those small peaks. And actually, this magnetic structure has already been found, I think, 60 years ago. It is actually the space group we found. And in this fig, we plotted both atomic structure and magnetic structure. We can see there is some magnetic moment at the nickel site. This small peaks result from the magnetic scattering, and this magnetic structure has twice the size of the subcell, which is the atomic structure. So that means that during the cooling process, because of the arrangement of the moments, so the antiferromatic structure is formed at a certain temperature. Nickel oxide is a simple structure, but it is a good start point for us. And then in the next step, Corey is going to show you more complex structure and recent research on this area.
Thank you. Oh, okay.
I'm fine.
Okay, good. Yes, so as Yang said, how do I get it to go forward, actually? Okay, good. I'm going to talk about a slightly more complicated example of what is currently being done utilizing HB2A, because I think we've all learned a lot about how to use different programs, and we've all learned a lot about what Bragg spacing is. So instead of spending the final talk on that, I thought maybe I'd talk about something you didn't know about yet. So last week, this paper came out in Physical Review B. The second author is Karina de la Cruz. She works in HB2A. She's really nice too, so if you ever have a chance to work there, I recommend you do. This is really interesting because it has to deal with frustrated magnetics. So what I'd like you to take from this slide, if you would look at these two different structures, they're the same formula. So we have our Ag2 chromium V042. So if you don't do a lot of solid state chemistry, that might be a little overwhelming, but it's okay. The only thing that's going to change is going to be this A, which will be silver, and I'm going to ignore potassium because it's just the middle case. Silver and rubidium are the two most distinct. So up here, when you have rubidium, we're actually going to have a nice even triangular lattice. They were kind enough to give us two different views, which you can find. They did synchrotron, but you can also have found this from some neutron data. So they give the sort of the BAC here, and then they give a top-down view where you can see the vanadium tetragonal vanadate complexes, how they connect to the chromium, the magnetic element, the chromium here. And then the silvers would be filling in these spaces. And then down here, the rubidiums would be filling in these spaces. And down here, silvers will be filling them in. As you remember, silver is much smaller than rubidium, so in order to make this structure work, the lattice, these these tetrahedra have to be tilted. And this is a small difference, but a very crucial difference when it comes to the magnetism. And it actually changes our space group. Our space group is P-3 for this one. And for the silver, it actually ends up being C2-C, so it loses its threefold symmetry. And this is interesting because you need that symmetry in order to have a spin liquid. This is due to a frustrated magnetic interaction. A frustrated magnetic interaction is an interaction where you can see here, these guys, say A and B, would love to be antiferromagnetic with each other, but they can't be fully sort of ferromagnetic because this guy's not facing in the same direction. So we have sort of a canting of these spins. And then this down here can give you a little bit better view of the exact interactions. We have these 6 different symmetry, like planes of symmetry, where you can see them flipping over, and the different potential spin interactions. But this honeycomb up here is what we're looking for in order to have our frustrated magnetism. Frustrated magnetism is interesting because there's a bunch of question marks on my slide, and it's not because I don't know the answer, it's because they actually don't have, that I've read so far, a practical application. But we're thinking they'll have some great applications in data storage and memory, or quantum computation, or maybe high temperature superconductivity, because it's something that hasn't been studied very extensively until pretty recently. So here's our silver case. Hopefully you remember from about 3 minutes ago, probably a minute and a half, I talked super fast. The distorted triangular lattice of the silver complex. And here, using our neutron data, we were able to, I say we, these people, I wasn't there. They were able to plot the magnetic data. And you can actually see here we have antiferromagnetic interactions. And there doesn't appear to be any frustration. In fact, they kindly took the octahedra animation or artistry out of these. So there's the chromium, and there are the 6 oxygens that it's connected to. But you can see this plane, and they're trying to highlight where you have the oxygens either closer to each other or farther away. That's our distortion. And depending on how that is hooked up to your vanadium, that'll be where your spin is going. And these spins are able to interact with each other. They're not facing each other. They're coming out of the plane at us. So we have 2 going down and 1 going up. We have an antiferromagnetic long-range order. And that is confirmed with our actual powder pattern. As Liang just showed you, here we have our Rietveld refinement of our Bragg peaks, and then coming down we have 20 Kelvin and 2 Kelvin. This ferromagnetic ordering, or antiferromagnetic ordering, happens at 10 Kelvin. So here we see our magnetic peaks showing up. And they were able to confirm that the ordering parameter of this compound actually fits what they predicted. So this study was to sort of show how you can predict whether or not you'll have a spin liquid or not. And they got pretty close to their theoretical value, which they were very proud of and emphasized strongly in the paper. I skipped this whole slide, and I don't know how to go back. So that's fun. How do you go back? All right, bye. Oh, wait, no, I think I got it. Okay, sorry. This is the most elegant talk I've given in my life. However, here's our rubidium case. So rubidium is larger than silver. We don't have that distorted. It's a non-distorted triangular lattice. And in a non-distorted triangular lattice, there are no magnetic peaks showing up. So, not only there are other data, they did magnetic susceptibility, they did specific heat, but I think that the clearest picture comes from this neutron data. And without neutrons, really they would have a lot of really good educated guesses, but here I feel like they've definitively shown there is no long-range magnetic order. They think it's due to the size of the non-magnetic spacer because, like I said, that was the only difference between the two. This causes our change in our orientation of our vanadate linkers. This is fully visualized by neutron scattering. So a summary of applications, you can do some interesting things. Structures with large interplanar spacing actually work well with neutrons, just to reiterate. Complicated magnetic structures, such as this. Phase transitions, thermal expansion, whole sorts of it's a very, very powerful technique. And this, is returning to manganese oxide. This is manganese oxide refined and refined and refined to find its preferential spin directions on an axis. And I also thought it was both pretty and aggressive. So thank you. Do you have any questions? We acknowledge this image has nothing to do with neutrons.
The intensity may change. So you would have to model your data. Yes, it's a rigor found.
Well, the intensity will change, but I don't think that you would have that. And if you know more than I do, please correct me if I'm wrong. Because the question was, can you have a magnetic lattice that matches perfectly your Bragg ordering, right? And I don't think that's going to happen because magnetic ordering actually involves a magnetic supercell. So you could have a similar pattern, but you'll have a different set of reflections.
That's not always the case. The magnetic cell can be exactly the same size as the nuclear cell.
I've never seen it before, and I felt really confident about that. But
that happens always for ferromagnets.
I haven't done a ferromagnet study.
And it often happens for antiferromagnets. Depends on where the sites are in the unit cell.
Do you want to guess how many refinements I've done successfully?
I don't know.
So thank you for telling me something. I appreciate it.
So what type of symmetry analysis do you have to do to constrain the possibilities of the magnetic structure? Do you know you determine the nuclear structure for how the atoms are arranged and what that lattice type is, what space group. What type of analysis did you do to constrain what the symmetry of the magnetic lattice should be?
Because we know the space group of the atomic structure, so we can look into the periodic table, not theoretic, crystallography table to find out the subcell of the atomic structure.
So generally speaking, is the symmetry going to be higher or lower?
Symmetry, I think, is lower, more symmetry elements.